The other is you can try to find a rough expression for a physical quantity in terms of some other physical quantity. So for example, the second one is assume a dependence of g, which is the gravitational acceleration, the length and temperature of the environment on the frequency of a pendulum, and find a dimensionally consistent form of the equation for the frequency. So, you know, if you have a pendulum of length L and of mass m, let's say, and over here the temperature is given as theta, and maybe and the gravitational acceleration is g, because depending on where you're doing this experiment, gravitational acceleration could change, right? So you have all these quantities, and you know that, you know, you can compute the frequency of the pendulum. I'm pretty sure in your high school physics classes, you've probably done this as an experiment. You hang a pendulum, you know, you just take it to the one side, release it, you start a stop clock, you know, you count the number of oscillations, and you see how much time has elapsed in the oscillation, and from that you can compute the frequency, right? And you repeat that experiment a few times to get rid of any statistical error, right? So let's say we're not doing that experiment. We have some idea that the frequency depends on the gravitational acceleration, depends on the length, maybe even the mass, and the temperature, okay? And we're trying to find out what that form is, what that dimensionally consistent form is. Now remember, we're not really solving the physics of the problem. This is not a physics problem we are solving, because dimensional verification technique will not give you the exact formula, but it will give you the general form. So like, you might find out that f is directly proportional to L, okay, hypothetically speaking, which means that if you increase the length by twice, the frequency becomes double. So we are looking for that general expression, but it is not going to be an exact expression. So how do we solve a problem like this? It's very simple. We're looking for the formula for a frequency, and we are already given that it is dependent on the gravitational acceleration, the length, and the temperature, right? But we don't know whether f is equal to g, or is it g squared, is it g cubed, or is it 1 over g, or square root of g? We don't know that, right? So let's say we have these unknown exponents for each of these quantities. So it's g to the power a, L to the power b, theta to the power c, right? And we don't know what a is, we don't know what b is, we don't know what c is, and that's something we need to find out. So if a is 1, if we can compute a to be 1, then we know f is proportional to g. If we find b to be 2, then we know f is proportional to L squared, right? If we find c to be 0, then theta to the power 0 would be 1. That means f is not dependent on the temperature. So we're looking for the values of a, b, and c. So how do we find it? It's really very simple. So all we have to do is we have to write the dimensions of each quantity. Okay, so let's do that. What are the dimensions of gravitational acceleration? This acceleration? L times t to the power negative 2. Why? Because acceleration is the rate of change of velocity. Velocity is L over 2. So L over t would become L over t squared. So that's L times t to the power minus 2. So we have L over t squared to the power a, right? Now notice that we have assumed the exponents, which we don't know what they are, right? If you don't write the exponent, then you're essentially assuming that exponents are equal to 1. If you simply write f equal to g, then you're saying a is 1, which you don't know. So for every quantity that you write in on the right hand side, make sure they have some exponent. If you have 4 quantities, you'll have 4 exponents, okay? L, of course, is a base dimension, so that's L to the power b. Theta is also a base dimension, so that's t to the power c, right? Because we can't write L and theta any further. So let's collect all the like terms. So we have L to the power a and L to the power b, so that becomes L to the power a plus b. We have t to the power minus 2a, and we have t to the power c. Right? No questions about this? So we have L to the power a times L to the power b, which is L to the power a plus b. So this is all in terms of base dimensions now. There's nothing more we can do, right? This is reduced to the lowest possible level. Let's look at the left-hand side quantity. What is the quantity on the left-hand side? It's frequency. What is frequency? It's number of oscillations over a unit time, right? So what is the dimension of frequency? T to the power minus 1, or 1 over t. So the dimension of the left-hand side quantity is t to the power minus 1, right? Now, if this formula is dimensionally consistent, then the right-hand side quantity should also have the dimensions as t to the power minus 1, right? So we need to compare these exponents on the right-hand side with the left-hand side. Since we don't have any m here, so we can write this as m to the power 0, right? Why do I need to do this? Because, well, maybe I will have m on the right-hand side. If I don't have m, then I don't need to worry about it. We have L over here. Since there is no L over here, so I can write that as L to the power 0. There's no theta on the left-hand side, so I can write theta to the power 0. Right? Now I have basically all of these base dimensions on both sides. So if both of them are supposed to match, then a plus b should be equal to 0. So if you compare this with this, we get a plus b equal to 0. If you compare minus 2a with the power of t, it's minus 1, so we get minus 2a equal to minus 1. And that right away gives you a equal to 1 over 2. Right? And if you substitute a equal to 1 over 2 in here, that gives you b as minus 1 over 2. And what is c? C is 0, because there is no theta term on the left-hand side. So we found all the exponents. That's what we're looking for, a, b, and c. So if you substitute these values of a, b, and c in your original formula, which is this, what do we get? We get f equal to g to the power 1/2, L to the power minus 1/2, and theta power 0, which is 1. So what we get is square root of g over L. Right? So if you remember the frequency of a pendulum from your high school physics classes, what was it? What is the exact formula? So you have factor of 2 pi, right? So exact formula is f equal to 1 over 2 pi square root of g over L, right? You didn't get that 2 pi, sure enough, because you're not really solving the physics over here, right? So you didn't get that 2 pi, but you at least got the dependence on some of the input variables. So what it is telling you is that f is proportional to square root of g, and is inversely proportional to square root of L. So if you increase the length of the pendulum to, let's say, 4 times, then your frequency would become, if you increase the length to 4 times, your frequency would become, new frequency would be half of the original frequency, right? If you did this experiment on another planet where the gravitational acceleration was maybe, I don't know, 16 times of gravitational acceleration of Earth, frequency would become 4 times. That's it. So you're essentially getting a general dependence of some of the input variables, but you're not getting the whole physics. So you can't use the formula that you obtained from dimensional verification technique and use that, right? Because you don't have that factor of 2 pi. 2 pi is dimensionless, so you'll never get it, right? Okay, so that's the general technique. Another example. This is the example from your textbook 3.6. Okay, so this is a drill bit, right? A drill bit that's supposed to create holes in parts, right? So when you drill a part, and if the part is moving, then that part can actually exert a transverse direction force. So transverse direction force is a force that's perpendicular to the drill bit, right? So if, let's say, you apply this force F, because the part that you're trying to drill hole through is moving in direction perpendicular to the length of the drill, then essentially it deforms the drill bit a little bit, right? So if the material it's made of is very soft, then it could deform more. If it's very rigid, it's thicker, then it's not going to deform. But to some extent, all materials will deform, right? And that deformation may be very small, but there is some deformation. So this is known as a cantilever, right? Because it is being held at one point, and you're applying this force. So you'll see this cantilever beam model a lot in your studies over here, okay? So now the question is, if I apply this transverse direction force on the drill bit, knowing the length of this, knowing the diameter of the drill bit, knowing something about the material property of this drill bit, can I compute what the deformation would be? And when you take mechanics of solid or strength of materials class, you will learn that there is a formula that gives you that deformation. So delta x, which is the deformation at the tip, because the deformation is changing along the length, deformation is given by 64 times FL cube over 3 pi e d to the power 4. Okay? So let's look at each of those terms. In the numerator, you have factor of 64, which is dimensionless. You have F, which is the force applied. So more the force, more the deformation, makes sense. L cube. So deformation is dependent on cube of the length. So more the length, more the deformation, but it's actually not directly proportional. It's L cube. So if you increase the length by twice, the deflection would be 8 times, right? Because it'll be 2 cube. In the denominator, you have factors that reduce the deflection. And what you have is the E. E is the elasticity modulus, which we'll talk about in maybe 2 classes from now. And elasticity modulus is a measure of the material property, how tough it is, what kind of material it's made from. So elasticity modulus for steel is different from aluminum, from plastic, and so on. And D is the drill diameter. And of course, you know that if the drill bit is made of thicker, then of course it's going to deform less, right? And that is d to the power 4, okay? So the question is, given this formula, can you say something about the dimensional consistency of this formula? Is it dimensionally consistent, right? That's the question. So it's easy to find. All we have to do is write all of these things over here on the right-hand side in terms of base dimension, and write the quantity on the left-hand side in terms of base dimension. If they match, it's dimensionally consistent, right? So let's do that. So F, let me write dimensions of each of these quantities separately first. So what are the dimensions of force? We know force is mass times acceleration, so that's m times. Acceleration is L times t power minus 2. L, of course, is L cubed, so L is L, so I don't need to worry about that. E, okay, E, which is the denominator, is elasticity modulus, and you're given the definition as force over length square. So that is the force divided by L square, and then you have the D, which is L, right? So let's substitute all this in. So we have 64 times FL cubed over 3 pi E d to the power 4, and we don't need to worry about 64 and 3 pi. They are dimensionless quantity. F is MLT power minus 2. L cube is L cube. E is MLT power minus 2 over L square, that's E. And then we have d to the power 4, so we have L to the power 4, right? Okay, so all of this cancels. This L square will cancel this to make it L square. So you will have L cube over L square as simply L, right? And on the left-hand side, you have delta x, which is the dimensionless length 2. Problem solved. It's dimensionally consistent, right? And you will see this technique being used in your fluid mechanics class, where you will come up with what are known as dimensionless numbers, which characterize the ratio of different kinds of forces. Anybody here in any fluid mechanics class or has taken a fluid mechanics class? So you're probably aware of Reynolds number, Prandtl number, Lucent number, and those are basically the ratio, and they're dimensionless numbers that are obtained via the dimensional verification technique. So you will see great use of this, especially in your fluid mechanics classes. Okay, but at least, you know, you can impress your friends. If they try to come up with a formula, you can tell them, hey, you know, what you're telling me is useless because it's not dimensionally consistent.